The objective of this presentation is to summarize my research work at University of Connecticut as a graduate student. My research work is primarily divided into three areas. The first one is electrospinning of biopolymers. Second one is encapsulating biological molecule in these nanofibers. And third one is electronic sensors based on conducting polymers. However, in this presentation, I will concentrate mainly on the electrospinning of biopolymers. To start my presentation, let me first introduce the technique I have used for making these nanofibers, that is electrospinning. Electrospinning is simple and versatile technique where polymer solutions are subjected to high voltage and stretching of this solution results into formation of nanofibers. The major advantage of this technique is that several polymers which cannot be spun by conventional techniques such as extrusion or wet spinning can be spun by electrospinning. The majority of biopolymers fall in this category. Our group mainly work in designing hyperfunctional fibers, and in the next slides I will give examples of these nanofibers which we spin in our group. The first example of such a nanofiber is biodegradable high strength nanofibers. These fibers are made up from specialty grade polycaprolactone, and you may appreciate that these thin and small nanofiber membranes can hold weight of glass slide, and they can also be stretched up to 8 times of their original length. The result of stretching this flexible nanofibrin was very fine alignment in the stretching direction. In the next example, we demonstrate formation of composite material. This composite material is made up with a aligned nanofibers layer on the top of microfiber mesh. Both nanofiber and microfibers are made up from the polylactic acid. We achieve this in a very simple way. We use the knit patterns of the micro mesh as a parallel electrodes required for alignment of nanofibers in the electrospinning. The particular mesh we use for this research is Hernier-Repair mesh, which is used for soft tissue reinforcement, and we anticipate that in the resultant composite we can take advantages of all, that is a microfiber, nanofiber and alignment. In these particular images, we show the fine alignment we have achieved during this project. We not only align the fibers across the knit patterns, but we can also align them between the interstitial gap of the micromesh. These composite materials are not only important for the tissue engineering application, but they are also required in the filtration industry or as a reinforcement composites, or also in the optoelectronic applications. In the next example, we show how we make nanofibers from DNA. This was the first image of nanofibers we have obtained from DNA. Neither the image or the samples were convincing that we can use them for any practical application. The right hand side image shows the digital photograph of self-standing DNA nanofiber mesh which we have obtained in the latter stage of the project. To make these self-standing DNA nanofibers, we have used DNase complex with cationic surfactants. By complexing the DNA, we have not only improved its processability, but we have showed that double helix of the DNA is retained by incorporating DNA intercalating dye. The detailed properties such as mechanical property and fluorescent property of these nanofibers can be found in our soft matter publication. The important property what we reported in that paper was the fluorescent enhancement in the nanofibers. What we have observed that DNA, whether it is in the film form or the fiber form, it gives more fluorescence than the conventional polymers such as PMMA. Overall, we have seen 100 times fluorescent enhancement when we compare PMMA films with the DNA nanofibers. These complexes of DNA are highly ordered structures, as they can self-assemble into lamellar morphology. Figure on right hand side shows the XRD pattern of the DNA nanofibers, revealing its structural regularity. If such order exists in these nanofibers, then we can use them to organize small molecule, especially if they are DNA intercalating or DNA interacting. Here we have used the same principle. We have used two dyes, one which binds DNA by intercalation and other which binds by minor groove binding. Such organization can lead to very efficient energy transfer between these two molecules, The left hand side image shows increase in the freight efficiency as a function of increasing accelerator molecules, and DNA plays very important role and acts as a ladder to organize these molecules. The details of these findings can be found in our Angewandte paper. And the beauty of this whole process is one can tune the emission color of these single nanofibers. Now on this the right hand side image shows various color which we obtain by using different thread dyes. The color varies from like yellow to red to purple to blue, and these all are excited at the same wavelength. The obvious extension of this work was the white light emitting nanofibers, and we have obtained them. The image here shows UV LED coated with the DNA white light emitting nanofibers. This white light emitting nanofibers was also covered in MIT's technology review, and they are well received in the industry also. In the next example, we show how we can make nano ribbons. These are made from the genetically engineered silk. The image on the left hand side shows I am holding a nanofiber mesh of the silk, and then the image on the right hand side is essentially the FASM image of these nano ribbons. The particular image shown here is a view of silk nano ribbons looked at an angle. They look very uniform, they are long, and they look like real noodles. The beauty of this all project is it is done from the aqueous solution. The shape of these ribbons is ideal for flat molecule encapsulation such as enzymes, and they have very high mechanical properties. We have published a detailed study on this investigation in Polymer. In the previous slides, we have demonstrated that we can make fibers from various biopolymers. These fibers have a wide range of application, including that for the biomolecules encapsulation, as a sensor, as an environmental cleaning material, or as an scaffold, and we continuously look to develop the application of these nanofibers. These are the few examples I showed are of my research work. Whenever I try to solve some problem, it creates new questions for me, and I keep on solving them, and that is the whole notion of my PhD thesis. Thank you very much for your attention.